Howdy folks, today I'm going to be talking to you about finding the volume of a solid of rotation. In particular, I'm going to be talking about when you want to use washers and when you want to use shells to find that volume. So, now the whole idea with a solid of rotation is that you've got some area, let's call it A, and you rotate your area A about an axis. I'm just going to draw it as a dotted line. Alright, so you get this weird looking solid of rotation. And we learned two methods for finding the volume of that solid. One of them was the washer method, the other one was the shell method. So washers was discussed in 7.2 of Stewart, and shells was discussed in 7.3, Stewart being this lovely book. So, now to find this volume, let's actually just back up to the area A. Because if you understand how to compute this area, you're going to understand how to figure out the volume obtained when you rotate this area about an axis. So when you're computing the area of A, let's begin by saying that A is bounded above by the function f of x and below by the function g of x, and that f and g intersect at A and B. And so when you're finding the volume, or rather, the area of A, what you can do is you can sort of approximate it by drawing a whole bunch of little rectangles inside of the area A here, like so. Now if you think about one of these little rectangles, say the rectangle at the point X that I've just labeled right there, the rectangle has a width dx, and it has a height that is f of x minus g of x. So its height is out here, f of x minus g of x, at that point. And actually, that's the same for every rectangle inside this area, right? So what you're doing is you're looking at a bunch of rectangles, all at different values of x, and they have height equal to f of x minus g of x, and they have width dx. So this expression is the area of one rectangle. Now you can imagine that if we add up the areas of all these rectangles in here, that we're going to get pretty close to the area of A. In fact, if we make dx as thin as we can possibly make it, so we let dx go to 0 pretty much, but not quite to 0 because then it would be kind of weird, well, then we get exactly the area of A, right? If we make these rectangles really, really thin, there's not going to be any error there. And hopefully you recognize this as an integral. So this is actually the integral from A to B of f of x minus g of x dx, and that gives you the area of A. Now, this is review. Pretty much everybody knows that the integral is the area under the curve, and you can think of it as a bunch of little rectangles. So, how can we use this to find the volume obtained by rotating A about some axis? So, I'm going to erase this and redraw it, because let's just think about one of these area rectangles, right? So, alright, so there's our solid of rotation again. Now, here's one area rectangle. We said we know that it has a width dx, and that it has a height f of x minus g of x. So if we take our area rectangle, well, when you think about it, as the solid, or rather the area A gets rotated into a solid, that area rectangle gets rotated with the rest of the area, right? I mean, the area here, area A, is the sum of the rectangles, so each rectangle is getting rotated. So if we rotate this rectangle, let's see what happens. look at the shape that the rectangle has traced out, right? We've taken our rectangle, we've rotated it around the same axis that we're rotating the rest of our area around, and it's traced out a washer. So this should clue us in to use the washer method. And as a reminder, if you want to review this, just go back and read it in Stewart, that then the volume of our solid is going to be pi times the integral from a to b of the outer radius squared minus the inner radius squared. And then we have dx or dy. That was our washer method. So, alright, that's cool. So now we've seen that if we look at one of our little area rectangles from just finding the area of A, it can trace out a washer, and that can clue us in to use the washer method. But what if we take our original area A and we rotate it around a different axis? Anyway, you get some kind of weird shape. Now, again, back up to your area slice. So here's your area slice. Same old. It's got a width dx, and it's got a height f of x minus g of x. And now take your slice and rotate your slice again. So, do this. This is going to turn up over there. So you can see that this rectangular area slice, when you rotate it around the axis of rotation that the rest of the area is getting rotated around, you don't get a washer anymore, you get a cylindrical shell. And a cylindrical shell being something that is cylindrically shaped, but it's actually really, really thin. It's not got any real thickness to it at all. It's sort of like a rolled up piece of paper if you want to think of it that way. And so that's your cylindrical shell. And I guess that should clue you in that since this rotates to a cylindrical shell, then you would want to use cylindrical shells for this. So, hopefully that made sense to you guys to think about the volume of a solid of rotation in terms of how the area slices of your original area are getting rotated around the axis, and to think about the shapes that those form. Now, there is a quick and dirty way to do this that's sort of a hard and fast rule, but I encourage you to take it from this standpoint, and you can actually derive the quick and dirty way if you understand this way. That's about it for me, so have a good night and happy mathing.